Hi, this is Coker presenting my final project for CS231A on reflection recovery and removal in photographs. Reflections are very common in photographs, and depending on the application, reflections may be a nuisance you want to remove or an interesting signal you'd like to isolate to explore further. Previous work falls into several categories. Physical solutions like using polarized lenses are not acceptable for everyday use with common mobile phones. Others have tried separating reflections from the background in a single image, but this is a highly ill-posed problem. The approach I'll discuss falls into the last category of multiple view recovery, where several different images are combined to try to separate the background and reflection. However, existing approaches use such techniques as optical flow, which assume that occlusions are opaque, and so are not able to deal effectively with combined background reflection pixels, which are a composition of two layers. This presentation explores a recently proposed idea called edge flow. The key observation is that edges typically belong to either the background or the reflection, but not both, since that would require the edges lining up perfectly between layers. Also, due to the scene geometry and the usually different depths of the background versus reflection, those layers move differently between views, so we can exploit parallax differences to separate the layers. So, how does this algorithm work? The user takes a series of images at slightly different viewpoints, and a reference image is chosen. The index T image can be written as a flattened vector and decomposed as a sum of warped versions of the reflection and background components of the reference input image. There is a different warping matrix, W, for the background and reflection layers because they move differently, but I assumed the warping matrix for a given layer was the same for all three color channels of a given image. The warping matrix is an n pixels by n pixels sparse matrix of interpolation weights. Note that the motion field for the reference image is all zeros and its warping matrix is the identity matrix. Alpha is the alpha mat and is a constant between 0 to 1 that describes the relative contributions of the background and the reflection components. The motion field between images is found by calculating the normalized cross-correlation for a window around a canny edge pixel to all areas in a second image. After determining peak centroids, the coordinate offset gives the relative motion for that pixel between images. Doing this for each canny edge pixel gives a sparse motion field. Some spurious matches are seen here. Next, I assumed that the background dominates, so edge pixels are more likely from the background. I used Ransack to fit a projective transformation to background pixel inliers. Then the remaining pixels must be reflection edge pixels or noise, so Ransack fits another homography to the reflection pixels. There are now separate sparse motion fields for the background and reflection. Next, I interpolated the sparse motion fields to get dense motion fields defined at every pixel. Each image is warped according to its dense background motion field so that all images are aligned to the reference image. Cycling through images, the background is almost completely stationary while the reflection layer slides over it. This shows how the reflection and background layers have been decoupled. Because the background and reflection components are assumed to be additive, we get an initial estimate of the background image at each pixel by taking the minimum value for that pixel over the image stack. There are still some obvious reflection components in this background estimate, for example the blue monitor at the top left, but some of the reflection is successfully removed. Remember, this is just the initial estimate. Similarly, the reflection is calculated as the pixel-wise reference image minus the estimated background image. For visibility, I've adjusted the contrast of the previous image. You can see interesting features of the reflection, like the coffee mugs and the letters on the board, which were indiscernible in the original input image. Everything so far was to get good initial values because now there is a large nonlinear optimization problem to get refined estimates of the background and reflection pixel values. We need to estimate the difference between each image and its decomposition into a background and reflection layer that are warped versions of the reference image. Some constraints are absolutely necessary, like forcing all pixel values in alpha constant to be between 0 to 1. Other constraints would probably be helpful, like constraining the gradient magnitudes and enforcing smoothness in the motion field vector components. Further conditions on the divergence and curl of the motion fields might also be interesting to try. This optimization can be done in a two-step alternating fashion. First, the motion fields are held constant by using their initial values. The system of equations is linearized and solved for the background and reflection images and the alpha value. Then those quantities are held constant and the system of equations is solved for the motion fields. This alternating procedure can be repeated over a few iterations. So that's how it works, and here are some references.